Hi, and welcome back to Integrated Science. I'm Miss Sparks, and today we are going to be breaking down how a wave looks in its behavior. So far we've been talking about energy and the law of conservation of energy, and how even our little micro connections between our protons and our electrons can cause energy to surge through a system with electrical static. And so we're going to look at what does that actually mean? What is the energy that is flowing through there? So we're going to look at how waves can travel through different types of mediums, and then how can we look at that quantitatively with some equations, and then qualitatively by describing. And so first off, we're going to start with just what is a wave? So a wave in general is just a repeating disturbance or movement that transfers energy through matter or space, meaning that it is a system that has the potential to move, to vibrate through energy, and then has the ability to go back down to potential energy. So think of it as like you're standing on the shore of a lake and you take a rock and you throw it in there. The water was calm, you threw the rock in, and then you got all those ripple marks. That was your disturbance, a repeating disturbance. You could see the energy going do, 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 all the way outwards. And so you created the movement that transferred energy. It sent a shift through the water. And so you created that energy there. It went back to potential energy as it got further and farther out, and then it got calm. The lake water got calm again, and then it was not disturbed. And so then you could throw another rock in and cause a repeated disturbance again over and over. So sometimes energy is always just kind of moving back and forth. So especially like electronics, they're always receiving some kind of message, or you could think about it as even like satellites. And then we can look at it at a really small scale too, just about how energy is moving through smaller systems. So we're going to look at both those kind of today. So first off, we have to understand that waves can travel through a solid, liquid, or gas. And so we're going to refer to this as what is the medium that the wave is traveling through. And so that is called the matter the wave travels through is called a medium. So you are hearing my voice right now, and it is moving through the microphone to get to your ear, and then transferring to your eardrum, and then to your brain. And so there's several different avenues that it's moving through, but it's moving through mediums, through a solid, a liquid, and a gas, possibly. Not so much a liquid. Hopefully you don't have some water in your ears, but a liquid and a gas, definitely. A solid and a gas, definitely. And so a medium can be either any of those states of matter. I'm also going to throw in our fourth state of matter, plasma, because we will get to our space unit where we will talk about energy being traveled through plasma, especially in the sun. The sun is actually a very loud, violent place. We just can't hear it because there's no medium in space, which brings me to this last point right here. So electromagnetic waves do not need a medium to travel through. So we're going to talk about all kinds of different waves, such as sound and light, even frequencies of different types of things, but some of them are brought to us by what we call the electromagnetic spectrum, and they do not need a medium to travel through, meaning they can travel through emptiness. And normally, once again, when we're talking about that, we're looking at space, things that are in between us and the sun, or us and the moon, or us and another planet 4 galaxies away, whatever it may be. So medium is the matter and energy travels through. So we're going to talk about our different types of wave processes. Our first one is just what we're going to call a mechanical wave. And a mechanical wave is any wave that requires a medium. So anything that needs a solid, liquid, gas, or plasma to travel through is a mechanical wave. Most waves are going to be mechanical. And so once again, sound waves, mechanical. If an earthquake would be a mechanical wave, water at the ocean is a mechanical wave. These are all different forms that need a medium and for it to travel through. Our electromagnetic spectrum is what we call a not a mechanical wave. It is something that is all on its own. So we either have mechanical waves or electromagnetic waves. And so our electromagnetic waves consist of oscillating electric and magnetic fields, which radiate outward at the speed of light. And so these are waves that are moving really, really, really fast. Our eyes are not equipped to see them, but we know they're there. These are our different types of electromagnetic waves. You can have radio waves, microwave, infrared. We do have some visible with visible light, UV, X-ray, and gamma. And if you take a look at this drawing down at the bottom, it gives you an idea. Some of these wavelengths we are accustomed to. Normally, we're not harmed by radio waves, microwaves, or infrared waves. But if you get over here, UV, X-ray, and gamma, you can see that the waves get much closer together and their distance is much shorter. And so these waves actually over on this side of the spectrum sometimes can kind of be damaging to our soft body tissue and skeletal structure. So we've all, or maybe hopefully not, but we've all been exposed to UV radiation due to just being here on Earth. The sun produces UV radiation that does seep through the Earth's atmosphere and we get exposed. If we're exposed too much of it, it causes a sunburn. And if you get more exposed even more over time, it ends up being possibly a skin cancer where you've damaged that soft skin so much. X-ray, if you've ever had one, normally they will bring in the big heavy cape and put it over top of you and only take a picture of whatever bone that you broke. They do that because X-ray is really, really, really strong in frequency and can cause tissue damage as well. And so they bring in the lead cape to kind of cover you up. So a wave front, let's kind of talk about that. That is the energy that is moving through the system. So kind of think of it as like ripples in water. So as the energy is moving through a system, if the source is not repetitive, it will kind of die out over time. But our wave front is where it carries the energy and it spreads out over time, meaning that it's that first big crest that's coming up. That is where all the energy is. So if we go back to here, we think about like our energy is like, then it stops, and then it's here again, then it's here. It's like kinetic potential, kinetic potential. It kind of keeps moving through this front, carries the same amount of energy, but can spread out over time. So if the energy source is constant, then there will be a constant wave front. If it dies down, then the wave energy goes back to zero. So there's two different types of there are two different types of mechanical waves we're going to talk about: transversal and longitudinal. And so a transverse wave is a wave in which particles of a medium move perpendicular to the direction of the wave it is traveling. So perpendicular is like moving this way. So if we think about what we have here is a picture of the ocean water. So the traveling wave is moving perpendicular, meaning it's kind of bobbing up and down, up and down, up and down. And so it's moving perpendicular. So transverse waves move perpendicular, bobbing up and down. So if you think about in the ocean, it normally looks like something's bobbing because it's moving with that wave front that is going across the water. The other type of wave is a longitudinal wave, and a longitudinal wave is where the particles in the medium are vibrating back and forth. They move parallel. So I think a slinky is a great idea. If you are able to hold a slinky and pluck it, you can normally see the energy moving back and forth, back and forth, back and forth. So a longitudinal wave is a wave in which the particles of the medium vibrate parallel to the direction of the wave. So we can see that this is where the energy is, where the slinky coils are compressed. And then when it's spread out, that's where it's releasing it back out. So it'll move back and forth, back and forth, back and forth, parallel. Properties of a wave are very important. So we're going to kind of go through these different properties and identify them. And then we're going to give them a qualitative and quantitative approach on how to look at them through this class. First off, crest and trough of a transverse wave is the peaks and divots, or peaks and low points of a wave. This is our crest. This is our trough. And in a longitudinal wave, that is our rarefaction, which is where it is spread out, and our compression, where the waves are really close together. So crest and trough for crest and trough for transverse. Ooh, got it today. And then rarefaction and compression for our longitudinal. We are going to spend time today looking qualitatively and quantitatively at wavelength. So wavelength is the distance from one peak to the next, or one wavefront to the next. And this wavelength gives us valuable information, which we can tell how fast an object is going, what is the velocity, what is the distance it's going to travel at, how much energy is moving through the system. So wavelength is going to give us, just by eyeballing it, we'll be able to give some qualitative information, and then we'll learn how to give some quantitative information on it too. Amplitude is another form of energy that is really important when we're talking about waves, and that is just the maximum distance the particles of the wave medium travel from their rest point, meaning that how high is that peak going up into the energy. So think of like a tsunami. A tsunami is going to have a high amplitude. It's water that is moving through the system, and it's bringing this huge wave, whereas just normally not so much. Or even on like a really stormy day at the beach or the ocean, the water is going to be really rough, and that's because the amplitude is going to be maximum. It's at its rest point. On a calm day, the ocean is very calm. You could look across and you probably don't see a whole lot of waves, but when a storm goes through, it really cranks up the energy and it cranks up the amplitude. There we go. So wavelength in general, let's go back to it and talk about it. So qualitatively, we can just describe like, oh, we can see that they're far apart, so that might mean slow. When they're really close together, they're going to be really fast. But there's also a way that we can look at that quantitatively. So wavelength is the distance from any point on a wave to an identical point on the next wave, from crest to crest. That's the way I always think about it. It's much easier that way, crest to crest. So wavelength equals our wave speed times frequency. So we want to know what is the speed of the wave and the frequency, and that can give us the wavelength. And sometimes we just have to measure it too. So we'll kind of get into what that looks like. I'm going to stop here. We are going to continue and talk about how to find wave speed and frequency and amplitude in our next little video. Thanks.